Hello community, today we talk about the RAG GPT failure. In my last video, I had here a beautiful malfunctioning on the RAG retrieval function with the new OpenAI Assistant API when we created our GPTs. And I wanted to verify that the retrieved information is really available, and it was not. So those GPTs failed. Today we answer why, what we can do, and how we move on. And I will show you where AI research is today. So here we go, let's start. I told you we had a look at OpenAI Cookbook, the GitHub examples, and we had a look at here at the Assistance API, the overview in Python, and we looked here at the Python notebook. Beautiful. And I even asked here my subscriber, hey, in my last video, we had some trouble and it failed. What do you think? And I said, do you think there's a difference between the code interpreter and the knowledge upload? And 1/3 said, yeah. Well, I don't think so. And I asked, hey, do you think another vector store, apart from the embeddings from OpenAI on the GPT-4 by OpenAI, would have performed better? And 12% of my subscribers said yes. Well, I will show you this is not the case. And then I said, hey, do you know why our RAG retrieval with the new Assistant API failed? And tell me in the comments. You see that 60% said, hey, they know, but nobody, and I mean absolutely nobody commented. So I want that you learn from this mistake, and this is a beautiful malfunctioning. Per accident, I live recorded this, so let's learn from this mistake. What do we have? RAG, vector space embeddings, creating by OpenAI with the new OpenAI Retrieval to create your own little GPTs. We do not need any external vector store, we do not need any LangChain, any Llama index, nothing. This is all handled now by OpenAI. But you remember, in the process, OpenAI applies here its own optimized tokenizer to the text. And OpenAI creates its own vector space, its own vector embedding, based on its own specific training dataset for GPT or ADA or whatever it has. And now the question is, and I asked you this in my last video, when does this in-context learning, when we give some examples in our return prompt to GPT-4, or let's call it RAG if the machine does it, overrides now the inherently pre-trained and fine-tuned knowledge of our GPT-4, GPT-small, whatever you have? When does it happen that our few short learning examples that we provide in the return prompt from a vector store, or if you write it manually, it's an ICL, overrides the inherently pre-trained knowledge that is encapsulated in the weight tensor structure of our transform architecture? And the second question was, why couldn't GPT find with its vector search, and this means the cosine similarity operation on a mathematically constructed vector space based here on the RAG data, why couldn't it find any correlated nearby vectors in the vector space of its pre-trained and fine-tuned vector space of GPT-4 example? And now the answer is very simple, because there were no similar vectors close by. Now, close by is a topological term that we need here for topological spaces, mathematical topological spaces. And we have here some beautiful topological tools to define in non-metric spaces where we have not a distance function applied to this particular mathematical space, that we can say we have a close by, a nearby something, if we talk about semantic similarity. So let's have a look at what happened in my last video exactly. And you see here a screen recording. And this is at 34 minutes and 53 seconds. You can check this out for yourself. I built here my own GPT. I uploaded here all the files here. And you see here only for code interpreter, I uploaded 5 Python and Jupyter notebook files. And I have activated my code interpreter. And in this first file, there was the solution. So I said, hey, show me the new assistant API command to generate the new assistant API now by OpenAI to generate my own personal little GPT. And just by accident, I clicked here when it was analyzing so that I could see here the Python code execution. And you see it was looking here, simple, in all the cells for a very particular string. And this string was OpenAI assistant.create in all cells. And the result of this was, it said, hey, there's no specific example of creating a new assistant found in the notebook, which is factually wrong, because in the last 30 minutes of this, or the first 30 minutes of this video, I showed you when we went through the complete API documentation of the new assistant API, contrary to the chat completion API from last time, that there is the solution. Very prominent is the solution over there. So what happened that we have here from the OpenAI, this is the old API structure, and then assistant create, this is the new API structure. Why do we have here an intermix? Now, let's have a very easy explanation. I give you a simplification. So, imagine this is our vector space that GPT-4 generated. And you have here 15 billion nodes, and you have about 100 billion edges from the neural connectome of GPT-4 between the different nodes. Now, think about here, if you want here, about the nodes here also in the vector space, and the edges here, the connectome, about 100 billion edges, with also specific parameters. Now you know, we have now two mathematical spaces merged in this simplification. We have all the tokenized sequences that are now built with a vector embedding engine into a vector space, and we have here vectors. Those are the nodes. And when we train an LLM, we learn the weight tensors that connect the nodes here, specific task. And now think about the edges as the weight tensors. So, to be strict, two mathematical spaces are merged here in one oversimplification. Great. So this is it, what GPT-4 is. And now what happens? Now we have the retrieval function, the RAG function, the retrieval augmented generation, where we have external information from the vector store, from databases, and we bring those texts, those code sequences, those numbers in. And we transform them to token sequences. And we have a specific tokenizer and. So our RAG-based token sequences, we now transform to vectors with our embedder. So within OpenAI, we have now the same, if you want, OpenAI vector embedding engine that creates now from our RAG-based documents here, the vector embeddings in a vector space. And here we go. And as you can see, it can happen, and this is exactly what happened to me last time, that there's no interconnect. This RAG here in white, this network here, was the new assistant API documentation. And it has completely new terms. The term assistant create or client beta create assistant does not exist in the pre-trained and fine-tuned dataset of GPT-4. So what does our vector embedder do? It cannot bring those dots into the familiar set, since those are complete new terms. Maybe not even that the tokenizer is able to put them in any vocabulary. So it builds here in the available vector space in a separate subspace of the vector space. It agglomerates here our RAG documents. And you see what happened? This new API documentation was so completely different that it occupies different subspaces. So we have here our RAG region, if you want, here in this very simple picture. And we have here our GPT-4 pre-trained and fine-tuned neural connector. And if it happens that you have new text, new vocabulary, new terms, new complicated formulations that are not in the fine-tuned datasets, you have no semantic context. The machine does not know how to translate one to each other. Because what we want is to have coherent subspaces, mathematical subspaces, where we have a metric defined. So we have a distance meaning defined in a topological space. So this is what we want. We want to have here clearly identifiable interfaces, where here our network dock on the other network. But this is only if those are very similar or only gradually evolving. This is what we hope for, but this is not what we got last time. I already did a video 1 month ago, this video where I showed you that Microsoft auto generation failed on RAG. And I give you an explanation from theoretical physics. I built a quantum analogon to explain you why multi-A auto-gen RAG fails. But it was a little bit too complicated, so today a very simple explanation. Now you see here that before I used here my particular question to create a new assistant API command, I had it summarize the content of the files. And this happened at 32 minutes and 05 seconds. And now my new GPT comes back from the retrieve document and says, hey, you can use now the OpenAI assistant create method. And here was the very first time where this interlink of the old pre-trained dataset, because this GPT-4 Turbo was or has a knowledge cutoff April 2023, and there was the OpenAI chat completion API documentation. So it started here with this old API, and then it tried to integrate the new API, but it failed. It created here something that does not exist, merging the old pre-trained and fine-tuned knowledge here with the new RAG knowledge. This happened, and this was the cause why this vector database failed, and why any commercial or non-commercial vector database or vector store will fail, because this is a system inherent failure. So whatever vector database or whatever expert system you built, it would have failed. Great. Yeah, of course, I showed you in the 30 minutes before, the correct term to create an assistant was client.beta.assistant.create. But merging this pre-existing knowledge that is embedded in its transformer network and giving here a RAG vector representation, you see what happened. It took the old OpenAI chat completion and merged it here with the last two terms of the new one. How can we imagine this in this simplified pictures? Now again, here we have again our GPT-4 or our GPT. And here we have those RAG-induced vector representation done by OpenAI in the OpenAI vector embeddings. And you see here, there is something close by. And also, we have maybe only one epsilon environment in our vector space where we can say there exists an epsilon. So we can build an epsilon environment in a topological space that we can say that this node from this network and this node from this network are coming within an epsilon. So there is a close by relation in a topological space where we can say, now our vector search engine says, hey, I found something. I found this point is close by to this point. And this is, I think, how this happened. This problem, this mistake happened in the very first place, that you have from the first network, this OpenAI command, and from the new network here, the other command, and it is merged. So you say, if this happens by accident, purely, you got a problem that the system cannot solve, independent what vector store you use, independent what vector database you use, independent if you use LangChain 100,000. There's no way this problem can be solved if you look here at this representation. Okay, now I was working in an oversimplified image to show you what I mean. So let's correct this picture and let's be a little bit more precise. Let's integrate the weight tensors. And you will immediately see what I did. You noticed that I told you that the RAG-induced vector representation is, of course, a vector representation. And let's say this is a two-dimensional space. We have here vectors, but there is no weight tensor indicating the strength of the connection of the edge between those nodes. So, to be more precise, please notice that there is an inherent difference. This RAG-induced vector representation has no weight tensors that are learned with ICL or machine-done RAG. Our GPT-4 has been pre-trained, fine-tuned, optimized. We have some reinforcement learning. So all their weights have been trained, adapted, optimized. So there's now a connectome where the knowledge is connected. Imagine like connected with the brain cells in the human analogon. We do not have this in our RAG-induced vector representation. In no vector store, in no application, you have here task-specific learned weight tensor manifolds here in a topological space. This is an inherent problem of RAG. So now we understand a little bit better what happened here. We tried to combine two really different systems, and we hope that our RAG system is so similar, is so semantically close, that those points try to merge almost into the network so that we have here a semantically closeness and we can operate with RAG. But if you have a new text or a new manual or a new API documentation with new terms, with new code segments, it will fail for obvious reasons. So let's think now, let's do a simplification again. All those dots that are not connected, but just a vector representation in a mathematically constructed vector space, let's say we put them in a RAG hyperplane. So in blue, we have a RAG hyperplane. And of course, our GPT network is now pink, and we call it a pre-trained and fine-tuned GPT based on the GPT-4 induced, yes, neural connectome hyperplane. So we have now, next simplification, we go for the network from the vector representation. From the weight tensor manifolds, we go now to two simple planes. In the pink plane, we have everything, the complete transformer architecture with all the learned weight tensors on the fine-tuning, on the reinforcement learning that we have a particular behavior of our system has been pre-trained, fine-tuned. Everything is there. The complete weight tensor manifold, let's say star coder 15B, has 15 billion free trainable parameters that have been trained and optimized, and you know what? This is pink. And then we have new code sequences that come in with RAG, with ICL, with few-shot learning commands in our prompt structure that go in now into our pink plane. But you know they have not learned the weight tensor, have not optimized the weight tensor. Those are just vector representation where we have a vector engine, a vector search engine operating in the blue hyperplane. And without any learned weight tensor manifolds. And this is the main difference. And so what this RAG hyperplane feeds back to our GPT system is only based on the external vector search engine of the vector store or of the S-BERT similarity, of a cosine similarity, of a Manhattan distance similarity, whatever you choose as a close-by measure. So this external vector search done on the vector proximity feeds now back 2, 3, 4 lines that are relevant here for the task that our GPT should do. But if we have now vectors that are outside of our neural connectome, it feeds back nothing, and RAG completely fails. It's a RAG disaster happening. And this is what happened in my last video. And it was by pure accident that I recorded it. I had a live recording of this mistake, and therefore I'm able to show you today my video now. So this is the simple reason why RAG fails. Or if you want to see a little bit more mathematical optimized, go to the video where I give you the quantum theoretical physical analogon to explain it over there. But you know, this failure is a great opportunity to learn how to improve, to make it better. So the next question is, hey, what we need if RAG fails here? What is the solution? Now, there's a very simple solution to cope with this particular RAG failure. You know the solution. But what is the systemic solution that we need for the next iteration, for the next evolution of, let's say, GPT-5 or these little GPTs in their next evolution? Now, we need here these additional hyperplanes with a learned weight tensor manifold. We need that those hyperplanes are not just vector representation, where we have an external vector search engine searching for relevant semantic information, but we need more. We need those learned weight tensor structures that build a neural connectome for a particular task. So our pink plane, as I told you, could be that it has the perfect English knowledge. It can speak English perfectly. And then for one particular task, we need here the learned and optimized weight tensor network tensor manifolds. And we need just one, but we need multiple of them. So for task 1, I switch in this knowledge plate. For task 2, I switch in a second knowledge plate. And if I have a real complicated task, I switch in the third knowledge plate. This is beautiful, and this is what we need. We need to stack here multiple weight tensor manifold and not multiple vector-based manifolds learned on specific tasks. So you see, this is the evolution why RAG now becomes obsolete. Now, I know there's billions of dollars invested worldwide in vector store, in RAG system, in retrieval augmented things, develop here re-ranking with cross-encoder and everything. But this is the commercial point for a commercial product that is now on the market. But we are looking into AI research. We are looking into the next step. And do you know what? The next step is already here. Because Stanford and Berkeley, and in the next video I will show you what are they working today already, what is their research going on. And we will look here, we have to understand before we understand what they're doing, we have to have a look at a highly new optimized CUDA kernels optimization, some new paging, some unified paging mechanisms for those stacking of knowledge blades. And in one of my last videos, I was talking about parallelism, about model parallelism, data parallelism, fully shorted data parallelism. We were talking about Hugging Face Accelerator. We were talking about deep speed 0-3 stage. And now we need something better, something even stronger, more powerful. And next time I will talk about a novel tensor parallelism strategy. And if we have these tools, if you understand what's going on, why we need this exactly for this stacked hyperplane with learned weight tensor manifolds, then I can show you what is now the new AI research by Stanford and UC Berkeley, and you will see what is the next step after those retrieval or retrieval augmented generation. Because as I showed you in my last video, it can completely fail, and all the GPTs you can build, there's no guarantee that those external knowledge that you upload with any vector store, with any whatever network you have, that those knowledge is really integrated into the weight structure, the weight tensor structure of our LLM or our VLM. Therefore, we need to make another step and go to the next technology that you want. And this will be the next video on Stanford University and Berkeley research, AI research, what is going on today, what they are developing, and where they are standing with this stacked hyperplane of learned weight tensor manifolds. Great! So you see sometimes some mishappening, some misfunction of a demonstration that you record live can lead to another video, to, I hope, an explanation video why this happens. And if we understand the elements of the system, we can understand why this failure in the system occurred. And it can give us an outlook to a better system architecture and to the solution. This is it for today. I hope it was a little bit informative, and it would be great to see you as a subscriber in my next video.